So, in this video, we are looking at a couple of examples of setting up integrals to find areas of regions in polar coordinates. So recall from the last video that the area of a polar region can be found by the integral from a to b of 1/2 r squared d theta, or r is the function of theta. So this would also be the integral from a to b of 1/2 f of theta squared d theta. So in this first example, we want to set up the integral that will find the area of the region that lies inside the curve r equals 6 sine theta, and that is the red curve. So trying to find the area that is inside the red circle, but outside r equals 2 plus 2 sine theta. That is the blue circle. So we are trying to find this moon-shaped piece here of what is that area. And if this feels reminiscent of area between curves, that's because it is. We have an outer area, which would be our red circle, and then the inner area that's getting subtracted off. If I just want to find the area inside the red circle, I could take the integral of 1/2 6 sine squared theta, and it would find the region inside the red circle. And if I just wanted to find the area inside the blue circle, I could do the integral of 1/2 2 plus 2 sine theta squared, and it would find the area inside the blue circle. And subtracting those two areas would give the area that's left. So in general, we already know that we want to find these two integrals where we'd have the outer area being the 1/2 6 sine theta squared d theta, and subtract off the area inside the blue. So 1/2 2 plus 2 sine theta squared d theta. What we need is these bounds, and these bounds are going to be the same. These bounds are the intersection points. Because we are dealing with polar curves where this is a little bit newer, we are going to look at a table of values to see where these intersection values might be, but we'll also see we can do the same thing we did before to find these intersection points. So first, finding some points on the red circle. I am picking out values that make sine either 0, 1/2, or 1. So we have 0, pi over 6, pi over 2, 5, pi over 6, and pi. When sine is 0, or when theta is 0, sine is 0. So that is the point at the pole. When theta is pi over 6, sine is 1/2. Meaning we would get a radius of 3. So of 6 times 1/2. When theta is pi over 2, sine is 1. 6 times 1 is 6. 5 pi over 6, sine is 1/2 again, 0. So here is the point 6 comma pi over 2. This is the point 0, 0, or pi 0. And hopefully we can find what this intersection point is. Plotting some points on the blue circle, or cardioid. I'm going to pick those same values because they're the same ones that make sine 0, 1/2, or 1. So 0, pi over 6, pi over 2, 5 pi over 6, and pi. And when theta is 0, R2, the blue function, 2 plus 0 is 2. When theta is pi over 6, we have 2 plus 2 times 1/2. That is 3. When theta is pi over 2, we'll have 2 plus 2. When theta is 5 pi over 6, we're back to 3. And then back to 2 when theta is 2. Meaning what points we have, this would be the point 2, 0. This would be the point 4, pi over 2. And this would be the point 2, pi. And you probably see it here. At pi over 6, both functions have a radius of 3. And at 5 pi over 6, both functions have a radius of 3. That does mean with this table of values, this is our angle pi over 6. This is the point 3, pi over 6. And this is the angle of 5 pi over 6. Making this point 3, 5 pi over 6. We have the two intersection points. We could do the same thing we did before in area between curves to find the intersection points as well. We're trying to find when is 6 sine theta and 2 plus 2 sine theta the same. So we would be solving the equation of 6 sine theta equals 2 plus 2 sine theta. This equation would simplify to 4 sine theta minus 2 equals 0, or sine theta equals 1/2. And the values of theta, where sine equals 1/2, are pi over 6 and 5 pi over 6. So we have those intersection points by either making a table of values and seeing if we can find that intersection, or by actually solving the equation. And the equation will definitely give us the points if it's one we can solve. But plotting some points can give us a good idea. So our integrals are supposed to be from pi over 6 to 5 pi over 6. And because they have the same bounds, we can combine them into one integral. So combining this into one integral, we will get the integral of 1/2 from pi over 6 to 5 pi over 6 of 6 sine theta squared minus 2 plus 2 sine theta squared d theta. And there is the integral set up that would find the region we wanted to. Let's take a look at another example. This time we don't have two functions, we only have one. We want to set up the integral representing the area inside the larger loop, but outside the smaller loop. So we want to find specifically this area. So again, to get a decent idea, what we'll want to do is set up a couple table of values. So in our table of values, I'm going to pick the things that make cosine 0, 1, or a half. So when we have theta as 0, we'd have r being 6, because 2 plus 4 is 6. When theta is pi over 3, we get 2 plus 2 being 4. So the points we'd have so far is here is the point 0, 6. At pi over 3, we'd have the point 4 comma pi over 3. At pi over 2, we'd have a radius of 2. And at 2 pi over 3, at 2 pi over 3, cosine will be negative 1/2. 2 times 4 times 2 plus 4 times negative 1/2 would be 0. So here is the first time we hit that 0. If we found the area from 0 to 2 pi over 3, we'd be finding this whole area above the x-axis. That means if I double that, it will be the whole area total. So entire area inside the big loop is 2 times the integral from 0 to 2 pi over 3 of 1/2 2 plus 4 cosine theta squared d theta. That gives us everything inside this loop. What we want to do is now get rid of this little loop. We want to only have outside the big loop. So now we want to find inside the little loop. So finding inside the little loop, I'm going to pick up at that 2 pi over 3 and say, what about at pi? At pi, we'd have 2 minus 4, because cosine is negative 1 at pi. So 2 minus 4 is negative 2, and that is this point on the loop. And then at 4 pi over 3, cosine is negative 1/2 again, and 2 plus negative 4 times negative 1/2 is 0. So from 2 pi over 3 to 4 pi over 3, we graph the inner part of that loop. So finding the area inside the little loop would be the integral of 2 pi over 3 to 4 pi over 3 of 1/2 2 plus 4 cosine theta squared d theta. So that gives us the inside the big loop and we also have inside the small loop. If we want to get rid of the small loop, we subtract it. So to find just this blue area shaded, we would have 2 of 0 to 2 pi over 3 of 1/2 2 plus 4 cosine theta squared d theta minus the integral from 2 pi over 3 to 4 pi over 3 of 1/2 2 plus 4 cosine theta squared d theta. Since these don't have the same bounds, we can't combine them into one integral. So we are left with these two separate integrals as our expression needed to find the area that is inside the large loop and outside the small loop.